My name is Martin Kristiansen. I was born and raised in socialist Denmark, but I live in LA now. I have a master's from Aarhus University in computer science, and I'm an Erlang engineer at Tiger Text. So any and all sort of spelling mistakes, I will blame on my Danish heritage, and but anything good and scientific, I'll sort of credit the university. I work at Tiger Text. We make secure HIPAA-compliant messaging and a bunch of services on top of that. And my plane ticket tells me that I should say that we're hiring. We are looking for any and all good programmers, especially people who like functional programming. So if people are looking, please come to us. We're friendly, and we actually have sort of fun, even though the subject matter that we're treating is a bit serious. So, my main objection when building in Erlang is that I am not a patient person. I really, really like the fact that I can model things quickly. And I can do that way faster in Erlang than I can in other languages that I came from. But it still feels slow, right? So the motivation for what we've done is to get to a point where we can quickly build big scalable backends even quicker than with normal Erlang. So this is sort of a stab at that. And personally, I have a sort of a belief that people have a tendency to try to over-optimize very early. Especially bright people will have a tendency to look at what they're building and make the assumption that they can do it better than anyone else, and hence not use any languages, and hence discover a lot of things on their own, which this might be an example of, but let's wait and see. And then I found that you often run into very, and I say PHP like in the nicest possible way, code in Erlang, where people sort of took usually Cowboy down from the shelf, and they started implementing handlers, and they never actually used the rest of OTP. They just sort of have this layer that goes to a data store and gives back results, which is nice if that's what you want to be doing, but often it's not. Often there are a bunch of constraints and race conditions that they just sort of forget about. What are we trying to solve? We're basically looking at, that was the thing that got me, looking at applications and trying to do simple data modeling. And what I mean by simple data modeling, and I hope I don't offend anyone, because I actually heard the opening talk on this track, and I would like to be able to draw boxes and generate code. That would make me happy. If I could draw sort of UML, that's short for Utopian Markup Language, right? If I could draw UML and generate code and then have something that actually worked, that would make me happy. I have not seen that work anywhere. But the closer I can get to that point, the closer I can get to just sort of making statements about the things and then having the rest of it semi for free, the happier I would be. Then I want to be able to do large-scale rollouts. By that, I just mean not toy projects. And then I would like some fault tolerance. I would like my application to have some of the features I like from Erlang. So why do we want to do data modeling? I would like, and again, this is perhaps a bit controversial in this setting, right? I'd like to have one source of truth for my data. I would like for any piece of data to know And by a piece of data, I mean something like, often when people build things, it's like an account. I would like to know what this account looks like. And I know that sort of goes against the whole CDRT way of thinking. But I would like that because it makes it simple and makes it easier for me to understand my application. And I actually think that in order to make semi-reliable and not full of bugs software, I need to understand what's going on. So I sort of want to have simple building blocks. Yeah, and that does mean that I would like to have one path of mutating data. And when I say one path, I mean one path for a particular piece of data. Again, an example being a user account. I want to have that live in one place and do updates to it in sort of one way. So I'd like the data modeling to be OTP-ish because I like OTP. And I really like gen servers, again, because they actually do what I talk about. They sort of encapsulate something, and then they work on that thing in a very sort of a local way. Yeah, and they give me transactions on my data, sort of for free. And I want that. I want that from my project. And that gives me encapsulation of whatever responsibility. If I've got a gen server corresponding to a user account, then that gen server is my source of truth about what that user account looks like right now. Yeah. And then I'd like to have sort of nice definitions and generic database mappings, just because I'm sort of lazy and I don't want to write that all the time. And you end up, or at least I end up spending a lot of my time writing database accessors, which is boring when you've done it 20 times. Yeah. And then we want some fault tolerance because critical applications just have to have it, and it's not an option to ignore it. It's not an option to just say one. Yeah. How are we planning on getting that sort of thing? We're going to be using the Raft protocol to ensure consensus on some shared states, or eventual consensus. And yeah, that's how we're going to be doing that. And yeah, the fact that we have this nice shared state means that we've sort of got a more global truth in our system. Yeah, first principles. I'd like what we're building, and I haven't even told you yet what it is, but we'd like it to feel like OTP, this sort of modeling tool for having things that interact with data. We'd like it to be simple, and when I say transparent, I mean I'd like that if you understood what a gen server was, then you'd also understand what this is. It wouldn't sort of require you to know a lot more. And then I'd like it to be easy to debug. Yeah. So now that was sort of the goals and the motivation. So we created something called industry. Yeah. And when I presented this last, I was told that there was a negative connotation to the word industry. And I said it's called industry because it's full of factories. And then someone said negative connotation on that word, but I'm guessing that's not the case here. Yeah. So what is industries? Let's talk about what a gen server is. A gen server is a PID that carries some state, and you can do calls and casts to it. Right? That's what you can do. You've got these PIDs. They're talking to each other. They're sending each other messages. That's all fine. And again, it's easy to understand. It's easy to model. What would we like? We'd like something that looks like it, except I don't really like talking about PIDs. I like talking about some kind of, did I just go backwards? Some kind of global ID. I like talking about account identifiers. I like talking about, yeah, again, for pretty much anything. I like talking about the ID that represents it, not the random PID it was assigned. I would also like to have this sort of backed by data, right? I'd like for this thing to be maintaining a copy of itself so that in case of crashes, like big crashes, I would be better off than if my Erlang VM machine sort of, if Amazon caught fire, right? Yeah, and the example again is this sort of user account that carries some state, and I want that state to be persisted to a data store, and I want that to be somewhat transparent, and I want to address it by the ID and not by the PID it's living on. So how do I get there? Again, I want to be doing some kind of call. I know there's a gen server behind it with a PID. That's fine. I want to be able to persist to storage. I introduce these factories, and hence the name industries. And what do these factories do? They're sort of they're the magic, right? They're in charge of making sure I've got a way to do these lookups from IDs to PIDs. They're in charge of making sure these things are actually alive and available. So yeah, it's sort of a factory pattern with some extra stuff sprinkled on it. But they're in charge of this. And then we can, of course, add more sort of optimizations if we want to be able to access the state inside the gen server. So how do we do that? First of all, we need to pick a data store to have this data persisted to. And now there's sort of a twisted argument that I never actually get right. So please, ask if it's nonsense. When you have a gen server and you have a state change, you want to persist that state change. So you're doing writes out to your data store. And you're doing them often, right? You're never actually reading anything because you're assuming that your state is right, which means that you're very, very write heavy, and you're not really sort of doing any reads unless there's a catastrophe. Which means that the fact that Cassandra likes writes and hates reads makes it your best friend, right? Because you can just push off all these updates to your running gen server, and Cassandra is fine, and it's fast, and it's good. So that's why we chose Cassandra. And then the next point is, well, how does this scale beyond one sort of machine, right? How do we have this table in place? And the answer that we chose is to basically have a Raft cluster that this attaches to, so that the Raft cluster can carry shared information about how to do this mapping, and the factories on the individual boxes can sort of course, talk to the Raft cluster. And there's already a nice implementation by Andrew Stone that does this. And when you look at that, the first thing it says on that page is not production ready. I beg to differ. It has flaws, but they're fixable. So yeah, you can get a nice Raft cluster with leader elections built in, with a commit lock that has, I think, unintended features. But it's good. So you can actually get that. Let's talk about Raft. Raft is about leader elections and distributed states, and it's based on timeouts. So basically the way it works is that you select a leader, and that leader then pings the rest of the cluster, and when the rest of the cluster haven't heard from the leader in a while, they start sort of initiating new elections. And it's amazingly easy to think you understand, then go back, try to implement, and realize that there might have been a few details you had to think some more about. But it's a nice and simple protocol. Then there is a shared state, which is basically this commit lock. And there are leader elections. So, OK, we've got that. That seems sort of bordering on trivial, right? We've got this factory. We've got these instantiations of whatever we had in the data store. We were able to persist to the data store. So what do we need? We need to look at that, right? We need to look at that conversion from our state to our data store. We need to look at the actual states, and we need to look at the data store. Those errors did not match. What would be a simple way of doing that? We could define a simple domain-specific language to just describe the state, and then we could write a translator and be done with it. So then the question is, what are these things that are in the state? And we call them entities, right? And it's basically a description of the thing, right? What does the thing comprise of? So a bag of attributes And yeah, it's basically a collection. It's a state. It's like a gen server state, except we can't really use gen server states. Because we want to know something about types that Erlang doesn't like giving us. Because Erlang was born without types, and then someone added them, right? Which made it something else. So we have to sort of come up with something real, right? We have to sort of say we've got these fields, but we've also got types, right? So we have to, or at least I believe, have to create our own types. So we did. This is sort of an example, right? We've got a bunch of attributes: ID, name, email, primary email, and we've got a bunch of types on it, right? And we defined such a grammar. It got quite small, which is basically we introduced a bunch of types. We introduced a behavior for these sort of workers that were the things that carried state that were gen servers before, but are now something else. And then we said, sure, let's start building these things, right? So this is what a schema for basically for the state of one of these workers looks like, right? It's the example from before, and it's the example I'll demo in a second. So we basically say there are some attributes, there are some options. The options are basically callbacks when things happen. Then there are timeouts, which means if I haven't been touched for a while, I can probably sort of kill that gen server and take it back later. And yeah, if you notice, we've sort of got complex things, which is we've got an ID, a name, and a last name, and then we've got these. In this case, this is an account. We've got these basic auth keys, right, which is a set of references to another module. It looks like this, which again has some attributes and callbacks, and has a reference back to that demo account. Yeah. Yeah. And turning these schemas into queries becomes quite simple. This really got small. Yeah. Basically, we were able to create nice tables from that description, and that is quite simple, right? It becomes just figuring out what the references actually reduce to. In the case of an account, it means going to the account and seeing what the ID is, and just building queries like that. Yeah, and we need to render types and things, but it's pretty trivial. The more interesting part is things like how do we create these things, right? If I want to create a new account, for instance, what do I do? Well, I have to sort of ask the factory to create it, which means go create an ID and then spawn a process and then actually set it in this edge table so that someone else can look it up afterwards. And then doing a call is sort of even more cryptic, right? Because that means looking in the edge table. If I can't find it, then go to the factory, ask the factory. Then the factory has to sort of figure out if it's actually able to load it. If it can load it, it can put it in the edge table, and we can try again. It becomes sort of interesting. But luckily, we can hide all of that, right? Because if we've got this in place, then we're able to basically do calls as if everything's addressable by an ID and not by a PID. And it does make it nicer and easier to talk about things. Yeah. So doing a call would look something like this. We've got a caller. He actually asks the edge table, figures out that there's nothing there, then asks the factory. The factory instantiates the worker, makes sure the worker's in the edge table, and the caller gets returned that you have to try again because we trust the edge table, and then the caller goes to the edge table. Yeah. So now I've got a code demo, which is an interesting thing. If I maximize this, will the world end? Nope. So this is our demo of how to use this. At first, there's some setup for making actual database connections. But down here, is that right? Yeah, up there we sort of walk through this. I'm sorry about the noise. We basically go to the two modules, get the schemas, then we append them, and then we throw them at this industries add factory, which from schemas generates factories. Then we can ask the factory to create an account, which basically means giving it a prop list and saying, I would like one of these demo accounts. Then we print the states. Then we sleep for 3 seconds. The only reason we sleep for 3 seconds is because we have a 1 second timeout, and we want to show that this thing falls out of memory. Then we actually go get the API keys of this account, because an account gets created with an API key. And then we check if the password is top secret, which it is by default. And if we look at the account code, we're implementing this behavior that we saw before. We have two calls. We've got get API keys and we've got print state. We've got our schema from before. And down here we see the timeout of a second. And then we basically have the callbacks, and then we've got sort of our known calls and casts from the gen server down here. And they have the same shape and form as we're used to. And then I'm using lager comments like crazy to be able to print things so that it becomes pretty for you guys in a second. Yeah, and we've got the same for our basic auth keys, these API keys. We've got the schema, and then we've got a couple of sort of trivial methods, one of them being this validate call that actually checks if the password was correct. Then let's try and call this thing. If we go to, industries, source, example, demo. It's not even the right thing. If we start it up. Yeah, this is when I have a small mistake, right? Because I have actually started this up in another window that I can't get to. In here, so let's just kill that. Let's move to that one. Sorry about that. Yes. Now I can start the server, and I can give you something that's actually viewable. And I could say demo go. And we did what we sort of said we would. And we can see that we started out creating some tables in Cassandra, because we did that automatically from the spec, just out of, created some tables. We then created some instances of these accounts. We created workers for them. We inserted the data into Cassandra. We printed the state. We then shut down, because we were waiting for 3 seconds. We shut down the workers. We tried to do something to the first worker again, which meant we did a select and loaded in from memory. And we printed out, it looks fine. And then we went on to do the same thing to the API key to check that it was the right API key. So that means that we were able to interact with it. If we look at if we look at Emacs again, we were able to interact with it as if it was a normal gen server, except we've got all these wrappers, right? But we were able to do calls to it as if it was a gen server, which was nice, and meant that we did not have to think about persisting it to the data store, and we did not have to think about all of that lookup stuff, because the library, the industries library, took care of that. I've somehow gotten my mouse lost. Yeah. That was the code demo. And then things that are missing, right? We don't have the Raft stuff in place yet, but it's coming. We want to sort of support fully nested structures, and by that I mean wide rows in Cassandra or nested things. Like I had a list of API key references. I would like to have a list of API key objects instead. That is, most of these things are trivial in the sense that they're not hard, they just take time. And we haven't spent the time yet. And then we'd like to have dynamic expansion of the tables as we go, as the entities grow. And by that I mean, if I change the schema, I would like to automatically update the data store definition behind me so that I could, so that adding a field to a state and having that persisted in data and having all the loading and saving became like a no-op. And again, simple, but haven't been done yet. And having wide rows. And then the fact that we have all of this living inside of a gen server means that it would also enable us to do a lot more sort of lazy loading. If we had a big set nested inside a gen server, we wouldn't have to load it until it was addressed. And the fact that we have our own function for getting it out of the state means that we don't even have to sort of have the user think about that. We could just know if it's in state yet, and we could load it as we go, which again makes optimizing global and not local to whatever you're looking at. So once we've got that in one thing, we'd have it across the board, and everyone would be happier. And then this was actually something I added 20 minutes ago, which was when I realized that even though we had a very specific use case for this, what we've done is sort of done just a persistence layer on gen servers, which was not what we set out to do, but actually what we ended up doing. So any OTP structure that carries state, we could do something like this too, right? Because what we've done is we've implemented an algorithm for figuring out the smallest delta we had to send to the data store when we did updates to the states, and that generalizes to most of these things, right? So we could persist everything if we wanted to. There's of course sort of a, do you want to persist the entire state of your running system? Probably don't, but you definitely do in some places, right? There are things that carry value and where you want to persist to another storage. And persisting our data in our gen servers to Cassandra means that you inherit, let's start with all the good from Cassandra, right? You inherit the fact that you now have, if you do sort of quorum reads and writes, then Cassandra is promising you consistency, right? Then you're happy, and then you can make claims about your system, right? Which I think it was when I took the functional programming class at university. We were asked how to implement recursion, and the answer was, of course, choose a recursive target language, right? Because then it's simple, then you're done, right? You can just sort of translate to that and you're fine. And this is sort of the same. If you're leveraging Cassandra's features, then you have them, right? The current limitations of Raft is that the current implementation allows you to only do reads and writes because of the whole commit log through the leader, which means that you basically got this one big bottleneck of a gen server living somewhere in your cluster. And that's, like, it makes sense for the writes, but I don't think I care as much about the reads, right? So if I got a persistent but not entirely up-to-date copy of whatever table I'm doing lookups in on the box I'm sort of running on, then I don't think I care. Because if I have to check a couple of places to make sure I can find the right one, then I'm happy. And the FSM implementation of Raptor does not have a nice way of figuring out if you are in the cluster, which means that you have to be a bit hacky to figure that out. But again, it's solvable. The upgrading of tables. I think I said that already, but we basically want to be able to do a diff of the definition that's in the data store with the one we'd like to have there, and either sort of generate a file that you can run, or just do it automatically. Probably generate a file that you can run for expansions, but not for destructions, right? So that you don't go dropping tables. And it's pretty simple, but haven't been done yet. And then we'd like these nested structures. And this example might be a bit sort of, nah. But yeah, currently all we have is these lists and sets, right? Which means that we're basically storing references like crazy to get this. And it also means that we have a lot of live objects. So what we want to get to is we want to get to a point where instead of having references, we can nest entire objects. And again, Cassandra totally does that. We've got wide rows. You can put things there. But we haven't done it yet. And it's, yeah, that's not as trivial as the rest of it, but it's OK. So basically, ending up in a place where a full list of nested structures can live inside an object. Yeah. And that's the same stuff, basically saying that we have these, yeah. And it's available there soon. Right now, it's got a bit of, what do you say? A bit of TigerText specific code in it that needs to go. But after that, it should be available for download and criticism. Hopefully constructive, but yes, criticism. Yeah. And I think that was it. Questions? Yes?
Did you take a look at JProg when you started this Raft thing? Instead of using Raft, having your management people, you consider using JProg, since JProg seems to handle this kind of scenario that you explained in a distributed situation?
So I did not look at JProg, but I got the same question last week. And then I looked at JProg, and to me it looks like JProg is more about sort of pub/sub setup, but I might be wrong. I did not look at JProg before doing this, but I can see how some of basically the lookup mechanism, right, is the thing that you'd replace.
Yeah. So yeah. I think you probably will replace the old ETS table you have there, and I think I don't know. I've not used it before, but I think you would replace the ETS table, and you don't need the Raft thing that you're doing by hand, since it's just the process dictionary that is distributed.
Yeah, I need to. So that depends, right? Because if you've got this lookup table, so you might be right.
It's a lookup table where you add a key to any Erlang process. So
yes.
You could just, whatever you pass as your key, you could always just do a lookup, and a lookup on the process dictionary is I think a O of 1 or something.
Mm-hmm.
So that's the first question. The second thing is, have you tried this against every load? Because it seems like if you have a billion records in your Cassandra DB, mm-hmm. you might have the prospect of having a billion processes, and they all have things they're all holding states. Mm-hmm. Don't you think, have you tried throwing load at this thing and seeing how it will behave? That's one. And then two, do you consider that you could be using up all your memory where you could have delegated work to Cassandra to do?
Yes. So, bunch of questions, right? The memory question.
Yeah.
So spinning up processes is not our solution might be very local to our problem space. But memory has not been a problem for us, and we run millions of users. But that might come from the fact that we are timing things that are idle out, and we don't have millions of sort of active right now users, right? So the fact that we have timeouts and that we pull these things, that we kill the gen servers basically, means that our memory footprint is smaller. But if we had sort of spikes in traffic, then yes, then that would definitely be a concern, right? Yeah. Yes. Yes.
Yeah. So, are you suggesting that you take the data inside the process thread? Like, if I want to do an update to a data structure, am I doing a get and then a set, or am I calling an update function?
So, the current implementation, you're thinking about complex things, right? You're thinking about lists and sets, right? So if you do an update to a set that's in memory, then I'll calculate the diff and do that update to Cassandra, right? So I won't be trying to persist. I won't take this giant thing and sort of shove it at Cassandra. I'll say, I know the state before, I know the state after, I know what you did of mutations, and I'll throw that at Cassandra, right? Which means that you are sort of pushing some of the heavy lifting to Cassandra. Yeah. You're not piping a lot of data, or not as much as you could.
Okay. So if you have like multiple processes trying to interact with this data structure, like if they both do a read and they both try to do a write, does that, like, are you just, how are you merging that data?
Oh, okay. So if I understand your question correctly, then I was not good at explaining what I wanted to do. So the whole point of this was that a data structure is owned by one process and one process alone, which means that only one guy is trying to do updates to this. That's sort of the invariant, right? So no two guys are trying to do updates to the same piece of data at the same time. That is sort of the invariant, right?
Sure. So like one process.
Yes.
But then multiple processes won't communicate with that process.
Yes.
Like they both want to do something with that data, so they both send a message to that process, right?
Yeah.
So is that like per set, or the two other processes doing like adds, or are they getting a full copy of the data and like trying to send a message?
They're doing the operation in sort of the gen service process space, right? So they're not fetching it, doing updates, and saving it again. They're sending sending like an add and having that run in the process space, right? Yeah, because the other thing would be sort of horrible. Yeah. Yes.
So what happens what happens when a process crashes in between when he has backed up things into his queue? Like, what do you do in that kind of situation?
When it's got things in its queue.
Like you fired an update message at the process, and the process acknowledges it. Like if it was a cast, you would acknowledge it immediately.
Mm-hmm.
And the person who sent the message, like you might run into like a MongoDB problem where you send the message to the process, and the process acknowledges that it's updated this thing, but then it's backed up in the queue.
Mm-hmm.
Because he has things to actually, probably you fired like 20 update messages at it, and it's doing a diffing and things like that.
Mm-hmm.
In between, if you have a crash, what happens to the...
So it would correspond to a normal, so basically it's just slower, right? It would correspond to a normal gen server crashing while processing, because this guy does not get to proceed on its mailbox until it's done with one cycle. So the cycle is just heavier, right? So if I'm doing one operation, then once I'm done with that, then that one operation is persisted, right? So it just sort of, it's the same problem as without, it's just slower, right? Did that make sense?
Sort of.
Okay. Yes? I don't see any hands. Then I think we're done.